Aerodynamic drag. I will discuss about the aerodynamic drag, which is one of the force which opposes the movement of the electric vehicle, or in general any moving body, that is the vehicle. A vehicle traveling at a particular speed encounters a force which opposes its motion. That is because of the air. So this force of the air is referred as the aerodynamic drag, and that is opposite to the speed of the vehicle. The aerodynamic drag has two components. One is the shape drag and another is the skin friction. The shape drag, we'll discuss about the shape drag. The forward motion of the vehicle pushes the air in front of it, but the air cannot instantaneously move out of the way, and its pressure is increased, which results in high air pressure at the front side of the vehicle. Now, air behind the vehicle also cannot instantaneously fill the space which is left by the forward motion of the vehicle. As vehicle has moved ahead, there is some space created. Now, this creates a zone of low air pressure behind the vehicle. The motion of the vehicle therefore creates two zones of pressure, one at the front, which is high pressure zone, another at the back of the vehicle, which is the low pressure, and the motion of the vehicle is obstructed, one by pushing, that is a high pressure in front, and by pulling it backwards, that is a low pressure at the back. So both the forces are opposing the vehicle. One is pushing back and one is pulling back. So the resulting force on the vehicle is nothing but the shape drag because of these two forces. This can be seen into this diagram where the front, which is opposing, creates the high pressure and pushing this back. On the behind, there is a low pressure zone which is pulling back. So these two forces will cause the shape drag. Now another force, which is because of the skin friction. The skin friction, the air close to the skin of the vehicle moves almost at the speed of the vehicle, so which is very close to the vehicle body will move, the air which is close to the vehicle body will move with the speed of the vehicle, while air away from the vehicle remains still. So in between, air molecules move at wide range of speeds. The difference between the speed between these two air molecules produces a friction, and that results in the second component of the aerodynamic drag, which is nothing but the skin friction. So with this resultant force or this resultant aerodynamic drag is the function of vehicle speed V, vehicle frontal area A, F, shape of the vehicle body CD, and air density rho. So we can summarize this and we can write it as aerodynamic drag Fw is equal to 1/2 rho AF, that is the frontal area, into shape of the vehicle body CD, and air density is taken, into V minus VW squared. So V is the velocity, that is a vehicle speed, and VW is the velocity or speed of the wind. VW is the component of the wind on the vehicle moving direction. It has positive sign when the component is in the same direction of the moving vehicle, and negative sign when it is opposite to the vehicle speed. So this sign will change based on the whether this wind is opposing to the vehicle speed, or it is assisting, or it is adding. So that will be decided by the sign of this wind velocity. Here are some drag coefficients for various shapes. So if it is a sphere, then drag coefficient is 0.47. If it is a half sphere, it is 0.42. For cone, now this is the direction of the air, so it is 0.5. For cube, it is 1.05. Angled cube, it is 0.8. Long cylinder acting on this direction is 0.82. Short cylinder, it is 1.15. Now there is a cube shape, and this is the cylindrical shape. So here the drag coefficient is larger. A streamlined body will show very lesser drag coefficient because of this shape. Opposition is less at the front area also as the back area of the vehicle. So it is 0.04. Streamlined half body shape, it will be 0.09. Some drag coefficient of vehicle bodies, vehicle body shapes is shown here. If we see the open convertible type of vehicle, coefficient of aerodynamic drag or resistance is 0.5 to 0.7. Van body, which is front area like this and back areas like this, and complete vehicle body is in this shape, then it is 0.5 to 0.7. Phantom body, it is 0.4 to 0.55. Wedge shaped body like this, it is 0.3 to 0.4. Now we can see this is the kind of a streamlined body, headlamp and all wheels in body covered under body. So it will have 0.2 to 0.25. Small case shaped is 0.23. Optimum streamlined design, it is 0.15 to 0.20. For truck, road trains, 0.8 to 1.5. Buses, 0.6 to 0.7. Streamlined buses, 0.3 to 0.4. Motorcycles, 0.6 to 0.7. So these are some indicative figures. It will vary when the shapes are different. Now this is the summary about the aerodynamic drag. Aerodynamic drag is having two components. One is the shape drag and another is the skin friction. Shape drag is because of the shape of the vehicle, where air opposition is there at the front end, also at the back end. But at the front end, it is high pressure zone is created, so it pushed back the vehicle, and at the back end of the vehicle, it is the pulling action of the air, so resultant force is opposing to the motion of the vehicle. And in the skin friction, there is a relative difference in the speed of the air, which is at the vehicle body, and air molecules which are away from the vehicle body. So there is relative difference, and there will be friction which is resulting to the aerodynamic drag. Now we will see the next opposing force, which is the grading resistance. When vehicle goes up or down on a slope, Its weight produces a component that is always directed in the downward direction. You can see here, if this is the weight component, it will have one component mg cos cosine cos alpha, another is mg, that is the sine component sine alpha. So one component is in the downward direction, another is the parallel. This component either opposes the forward motion, that is the grade climbing, or helps the forward motion, grade descending. In a vehicle performance analysis, only uphill operation is considered. So in the uphill operation, you can see this is opposing to the vehicle moment if vehicle is moving on this. So mg sine alpha, this is exactly is opposite to the vehicle direction. If we see vehicle is moving in this direction, then mg sine alpha component will have force which is opposite to this direction. Thus, grading force is usually called grading resistance, and it is given as Fg, that is grading force, is equal to mg sine alpha, that is mass into gravitational constant into the sine of this grade or slope. To simplify the calculation, the road angle alpha is replaced by the grade value when road angle is small. So for small road angle, we can define it, grade can be defined as I is equal to h divided by L. So here h is the slope height, and here is the length of that road or slope. So it is taken as tan alpha, and as it is small, you can equate to sine alpha. In some literature, tire rolling resistance and grading resistance together are called road resistance. So rolling and grading resistance, they are combined and called as road resistance because it is related to the road, and it can be expressed as FRD is equal to FF plus FZ. So resistance, road resistance is given by these two terms, and that is for the F, that is the front, and that is for the rear. So it is mg fr cos alpha plus sine alpha. These two components, that is a rolling resistance and grading resistance, or these rolling forces or grading forces. Now these values are kept here, and you can get this one is the sine alpha and another is the mgfr cos alpha. When the road angle is small, the road resistance can be further simplified. So the road resistance FRD is equal to FF, that is the rolling resistance, plus grading resistance, that is mgfr, which is simplified here. This term is taken as fr, and sine alpha is now taken as a I, that is the grade here. If you see the total dynamic equation, considering the different forces which are opposing to the vehicle, in the longitudinal direction, the major external forces acting on two-axle vehicle include the rolling resistance of the front and rear tires, that is FRF and FRR, which are represented by rolling resistance moment TRF and TRR. Aerodynamic drag is indicated by FW. Climbing resistance or grade resistance Fg, that is nothing but mg sine alpha, and tractive effort of the front and rear tires. This tractive effort is given by basically the engine or the motor, which is the giving motion to the vehicle. So it is F FTF and FTR. FTF is 0 for a rear wheel driven vehicle, whereas FTR is 0 for a front driven vehicle. Because as it is a rear wheel driven vehicle, force is applied to the rear wheel. So torque on the front wheel or FTF will be 0. Similarly, for the front wheel driven vehicle, the force on the rear wheel, that is the tractive force on the rear wheel, FTR will be 0. The dynamic equation of vehicle motion along the longitudinal direction can be now expressed as m dv by dt, that is nothing but the force FTF plus FTR, which is the tractive force on the front and on the rear, minus the opposing forces, that is FRF plus FRR plus FW plus FG, that is the rolling resistances, force, dynamic, aerodynamic force, aerodynamic drag force, and grading force. So these three forces are now there. Here for each wheel, if it is a front wheel, you will have the front wheel tractive force, rear wheel tractive force. So we get this equation as the dynamic equation of the vehicle moving along the longitudinal direction. Now here dv by dt is the linear acceleration of the vehicle along the longitudinal direction, and m is the mass of the vehicle. The first term on the right hand side of the equation 5 is the total tractive force, this term, total tractive force, and the second term is the resistance. So this will have the all three resistances, 1, 2, and 3. There is the rolling resistance, aerodynamic drag, and grade resistance. The maximum tractive effort and powertrain tractive effort also can be seen. So here in the graph, coefficient of friction is shown, and here is the slip ratio is shown. The maximum tractive effort of the vehicle is proportional to the slip ratio of the tire, which represents the difference between the angular tire speed and the vehicle speeds. So there is the angular speed of the tire is different than the vehicle speed, because whatever speed is with the tire, the same is not used for the vehicle speed. So there is some slip, and which is the speed of the vehicle is lesser than the tire speed. During the acceleration, the slip ratio of the front and rear tires can be expressed with this expression. So rho r is equal to r wr omega r minus v into r wr into omega r for the rear wheel. That is the slip ratio we are calculating. For the front, omega f is equal to r into r omega f into omega f minus v divided by r omega f rwf into omega f, where rwf and rwr are the radii of the front and rear tires, and omega f and omega r are the angular speeds of the front and rear wheels. Slip friction coefficient characteristics of tire have a nonlinear relationship and depend on the road surface conditions. So this coefficient of friction and slip ratio are shown in this graph. This is the typical tire slip ratio friction coefficient characteristics. For ice, we can see this is the slip ratio. For snow, you can see this is the slip ratio with reference to this baseline or zero axis. Then for weight, you can see this is the coefficient of friction, and slip ratio will go on changing. Similarly, for normal conditions, you can see the coefficient of friction is increased and the slip ratio is increasing. The sum of torques on the each wheel determines the rate of change of wheel speeds. So torque is acting on the wheel. So if you see this, J omega Jf is equal to d omega f by dt equals Tef minus Trf, where Jf and Jr are the inertias, Tef and Tr are the traction torques delivered from the drivetrain. Trf and TRR are the reaction torques due to the tractive forces of the front and rear tires respectively. So we can see the torques, the front and rear wheels. Similarly, Jr into d omega r by dt, that is the rear wheel, that equals to the TER, the traction force, TER minus TRR, that is the rear wheel, and this is for the rear wheel, which is the one is the reaction torque and another is the traction torque, which is applied by the engine. The reaction and friction torques on the front and rear tires can be calculated now. TRF is equal to RWF into FXF, and TRR is equal to RWR into FXR, where RWF and RWR are the radii of the front and the rear tires, and FXF and FZR are the normal forces acting on the front and rear tires. The traction torques on the tires TF and TR are provided from the powertrain. These are the traction forces on the front and rear wheels, which is given by the powertrain, given by the engine, or given by the motor. If the vehicle is a rear wheel or front wheel driven, the non-driven wheel provides no traction torque. So whenever engine is coupled to the front wheels, it will provide the traction torque. If it is connected to the rear wheel, it will be provided by the rear wheel torque. Therefore, for non-driven wheels, Jr d omega r by dt is equal to minus RWR into FXR. In conventional vehicles, the sources of the traction torque is the internal combustion engine, and the output power of the engine is supplied to the tires through the clutch, the transmission, and the differential gear. Therefore, the traction torque applied for either a front or rear wheel drive can be expressed as TP is equal to TEN IT I0 into epsilon P, where TEN is the torque from the engine, IT is the gear ratio, I0 is the gear ratio of the differential, and epsilon P is the total efficiency of the powertrain. So these terms will give the total traction torque applied to a front or rear wheel. So we have discussed about the total dynamic equation, which consists of all the forces acting on the vehicle and the tractive torque. or tractive force.